Hello, everybody. I hope you enjoyed the mentorship tables and everyone is back in the auditorium for our next talk. The next talk is given by Olga Kapralova, and she is a lead engineer here, a manager in Google Assistant in Zürich. And she leads a team of 20 plus engineers developing Google Assistant. She has received her PhD from the University of California at Riverside in electrical engineering, and afterwards she joined Google, but in New York, working on speech. And now she's here with us in Zurich. So Olga, you have the floor, and we're looking forward to hear about your journey from coding theory to Google Assistant.
Thank you, Christina, for the introduction. Hello, I'm Olga, and just in this talk, it will be, I'll describe my journey right from coding theory to Google Assistant. So, as the title line says, right, I started this journey in my undergrad with a very strong interest in information theory and communication systems. And I developed this interest by obtaining a PhD in coding theory. Right, so how are these two connected? Well, communication theory, communication systems, right? You need to transmit the data efficiently over a noisy channel. And this is exactly where coding theory steps in. Essentially, in coding theory, you have a bit string, and you need to transmit it efficiently over the channel so you can recover the data on the receiving side. And the natural way how people have been doing that is by introducing the redundancy into the transmitted message. And in my PhD days, I focused on read-male codes. And look, I know this conference is not about codes and it's about data science, but for the sake of completeness, let me tell you about what I did in my PhD. So like, why? Well, because it's fun. So there would be, and it's interesting. And so there would be some polynomials on the next 3 slides, but I'll get to data science after that, I promise. So yes, in my PhD, I focused on read-male code. This is constructions that were introduced in 1954. So as you can imagine, they're extremely well studied. And why do people like them? Because they have polynomial structure. What does it mean? In read-male codes, messages are polynomials. And redundancy is introduced in a natural way. These polynomials are evaluated on all possible entry points. For example, imagine your message is this polynomial in 3 variables of degree 2. For example, x2, x3 plus x1 plus 1. So this is a code word in read-male code with degree 2, right? And with 3 Boolean variables. And if you write, essentially, if you evaluate this polynomial on all kind of triplets, right? So there are 8 of such triplets, you get a code word. Simple, easy. And again, these codes have polynomial structure, which allows for analysis, for interesting analysis, and also it allows for very efficient decoding algorithms. However, these codes have drawbacks. And one of the major ones is that they have low rate, which means that they just introduce too much redundancy. And in my PhD, I focused on the following problem. Can we construct codes of higher rate that still keep this polynomial structure? And that's why I enjoy all these nice recursive decoding properties. And the natural idea is the following. Let's take polynomials, but let's evaluate them not on the entire hypercube, but on a subset of it. And we started considering Hamming spheres. Hamming spheres can be defined in a simple way. So you take all your sequences of variables, let's say x1, x2, x3, as in the example, and you only evaluate it, and you only take those that have specific number of ones in them. Let's consider an example. So take the same polynomial, x2, x3 plus x1 plus 1, and if you want to consider it on a sphere of radius 1, this is essentially depicted here in this blue triangle, right? So you take triplets of with just one in them, and this is your code word, or if you look at essentially sphere of radius 2, you take triplets with 2 ones in them, and this is your code word. So I won't go more into details here because it's just lack of time, but essentially what I did in my PhD days is I analyzed error correcting properties of this code, developed efficient decoding algorithms, and showed some nice results. Okay, and now, as promised, I'm going back to data science. So after my PhD, I wanted to focus on something more applied, and that is highly kind of developing area at the moment, and of course, is machine learning. And information and coding theory, like the mathematical apparatus, is extremely relevant to machine learning. And that's why in 2013, I joined speech team in Google New York to work on speech recognition. Okay, just I think it's a good idea to give a high-level description and of how speech systems work. So the goal is very simple. You're given a human speech and you need to transcribe it into text. So, and here are the major components of the system. So first, this continuous waveform is transformed into a set of finite length feature vectors. After that, the sequence of feature vectors passed to the decoder, and decoder outputs the text. And decoder here, of course, it has underlying decoding algorithms, but if you look at kind of its building blocks, it consists of 3 major ones: acoustic model, language model, and lexicon. And I was focusing on acoustic models. Acoustic modeling has been relying on neural networks for, I think, at least 10 years right now or so. And one of the projects that I worked on is, okay, how can we improve the quality of acoustic models? And this is what we have done. So this work is from 2014, so it's almost 7 years old. Of course, current systems are different, so please take it with a grain of salt, but this is what was relevant at that point, and it actually was deployed in production, and a super interesting idea, I think. So let's start. Now, what I did back then is the following. Okay, so we wanted to train, the goal was, how can we obtain higher quality acoustic models? Okay, we needed training data, right? Training data is key often when you need to train high quality neural networks. Okay, how to get it? At that point, the process that was used is the following. So there was a real-time production system, recognition system, right? That was writing anonymized logs. So what we were doing at that point is we were taking a lot of data from it, 50 million utterances. After that, this data was manipulated to carefully select 2 million out of it, and this was used as an input to the training system. So what was the problem with this procedure? Well, first is that production system components are constantly changing, and of course, there was a non-uniformity in the transcription quality. But the major problem was actually not even that, but that we were trying to get something better out of transcripts of a quality of a system that exists right now, right? And so, of course, we focused on how can we get better quality training sets. And what did we want? We wanted it essentially, obviously, 2 things. Well, we wanted high quality data, and second, it never hurts to have more data. And this is what we focused on. So getting more data at that point was easy. We are Google, right? Yes, we have logs. So we were, at that point, I decided to sample 300 million utterances, which is actually more than 20 years of human speech. So a lot from our acoustic logs. And then I had to construct high quality transcripts for these utterances. How it was done? You know, this is an offline system. So I realized, okay, there is no need for me I can construct a high quality system, just which would be much slower. But since it's an offline process, it doesn't I'm not limited by stringent latency requirements. And after that, I will retranscribe these 300 million utterances, and I will select carefully a new training set of a larger size. So here's how it was depicted. So there was this production component as before, it's still writing logs, nothing changed there. After that, I went to logs, extracted more data, and I constructed this offline redecoding step, which I will describe in a minute. It is a slower system with a high accuracy I was reprocessing this data to get redecoded utterances, after which I carefully selected samples that I used in my new unsupervised training set. So what was so different, right, in this new system? First, I significantly relaxed decoder parameters. So if you think of what does the decoder do, right? On a high level, you can think of it as decoder keeps in memory a set of candidates. Each candidate has a probability. And the decoder then has to decide which one to select. And of course, the more candidates you can keep in RAM at the same time and recalculate probabilities for, the higher accuracy you can achieve. So that's exactly what I did, right? I made the decoder slower by increasing the so-called beam width, a number of active arcs, essentially, that I was allowed to traverse during the search time. Second, I trained new and much larger language models. So at that point, production system was using 15 million engram model. I changed it to 100 million engrams. And third is when I was building, training these language models, I essentially make sure that I exclude these samples in which I would be training acoustic model from this sources of a language model to make sure I don't introduce the negative feedback loop. And if we look at high-level comparison of this production and the redecoding components, you can see that. So here I list for 4 languages that I did back then. So I achieved, so WER here is word error rate. Essentially, it just shows how accurate the transcript is. And I achieved a higher accuracy, so from 5 up to almost 12% high accuracy, but of course at the expense of time. So the redecoding step was much slower. It was from 2 to 5 times slower. But so to recap, right? I constructed this slow system. I used it to retranscribe utterances. I got high quality transcripts, and then I selected a subset of them, a big subset, 20 million, and I trained new acoustic model on this data. And I achieved in the final production system a significant gain on performance, 2 to 3%, and this was deployed in production across multiple languages. So this is one of the projects that I did in speech. And after that, if I look back on my journey, this was a new step in my career. I transferred to Google in Zürich, where I started working on the Google Assistant. And specifically, I have been working on assistant suggestions there. So essentially, these are chips that are shown either right below the answer or before the query. And they essentially represent possible follow-up queries or actions that user can do with Assistant. And naturally, of course, there is a lot of tools that we use in machine learning for ranking, for generation. But unfortunately, I don't have time to talk about it right now. So please, and that's why I stop here. Please let me know if you have questions. I will be happy to answer them. Thank you.
Thank you, Olga. Thank you for going through your journey with us. That was very interesting how the fields that you worked in changed, but still kind of the same skills apply.
Exactly.
So we received some questions on the Mentimeter. So I'll start with the first one. Does this anonymized utterance data that you presented on slide 7-8, is it available for the public for more research?
No, unfortunately not. Not.
Yeah, it's usually the case that companies have their own data that they extract, that it's usually not available. And some of the corpuses are made public. But...
Some of the corpuses are made public, right? For speech recognition, there are canonical corpuses, right, that are used for academic research, but unfortunately, this data set is not available.
Thank you. Second question. Were there any requirements on the resulting acoustic model size, and did it have to work on device? And if yes, were there any other requirements for that?
So yes, there were, of course, requirements for acoustic models on the parameter size and on specifically its latency. I think at that point, for the sake of experiment, I didn't change the network architecture. So I use the same sorry, architecture as production system, but I explicitly only changed the input data set to make sure I don't add up too many changes at once. This model was not for on-device deployment. Of course, requirements are different, right, for server-side and on-device, because server-side has more computing resources. So here we were not focusing on on-device, it was server-side.
Thank you. Another question, where do you see Google Assistant going on? What would be the future of Google Assistant?
Great question. Lots of interesting ideas. If you're interested in that, please come to Google and work with us. But essentially, it's, there are so many different services for Google Assistant, right? It exists on your mobile phone, it exists in like Google Home, on smart displays. So different future for different surfaces, but yeah.
Thank you. Okay, so thank you, Olga, again for joining us today, and thank you for your talk.
Sure. Thank you so much for having me.